Okay, so the first question we have is, a complex electronic device contains three components, A, B, and C. The probabilities of failure for each component in any 1 year are 0.01, 0.03, and 0.04. If the components fail independently of one another, what is the probability that the device will not fail in 1 year? So we are given the probabilities of failure, and we want the probabilities of success, basically, because it says that the device will not fail. Okay, so we're going to calculate the probability of A not failing. We're going to multiply it with the probability of B not failing. And then lastly, multiply that probability with the probability of component C not failing. And we're able to multiply all of these together because these are, in fact, independent events. Okay, so probability of not A failing is 1 minus the probability of A failing. So we're going to put our complement rule to use here. And just do that with components B and C as well. And we end up with our answer of 0.922. Choice D. So again, an important reminder is that we're using the complement rule. And we can use the complement rule for probabilities with the word not. Okay, let's move on to question number 1. So the SC Electric Company has bid on 2 electrical wiring jobs. The owner of the company believes that the probability of being awarded the first job, event A, is 0.75. The probability of being awarded the second job, event B, is 0.5. And the probability of being awarded both jobs, event A and B happening, is 0.375. If the owner's beliefs are correct, which of the following statements must be true concerning event A and event B? Well, first of all, we want to ask ourselves if both events can happen at the same time, to see if they are mutually exclusive or not. So again, mutually exclusive means that they cannot happen at the same time. So mutually exclusive is cannot happen at the same time. Okay, so that means that not mutually exclusive means that they can happen at the same time. So, what do you think? You can pause this video and consider this for about a minute. And I'm just going to highlight this over here as a hint. All right, so because we know that event A and B happening at the same time is in fact not 0, it is 0.375. That is in fact not equal to 0. Then we know that event A and B happening is possible, and so it should be not mutually exclusive. It can happen at the same time, so we're going to cross out A and B. So we are now down to C, D, and E. And now we have to consider the independence part of it. So let's take a look to see if they are independent or not independent. Independent or not independent. And the last one says that it cannot be determined with information given. Well, to determine if two events are independent, remember that our conditional probability is probability of A given B is equal to the probability of A and B happening divided by the probability of B. So the bottom is always our given. And if we cross multiply, right here, when we cross multiply, we actually end up with probability of A and B happening is the probability of A given B times the probability of B. Well, what happens if we don't care about our given B? Well, if independent, if these two events are independent where the results of the probability of A happening has no effect on the probability of the outcomes of probability B, if independent, then we really have probability of A and B happening as equal to just probability of A times the probability of B. Well, is that true? Let's take a look at what's given. So we are actually given the probability of A and B happening. It's right here. They tell us it's 0.375. So all we have to do is just plug in that information. So let's go here and plug in that information, 0.375. And we got it right from the problem right here, 0.375. They also give us the probability of A happening, and the probability of A happening is 0.75, right there. So we're going to fill that out at 0.75. And we are going to multiply that with the probability of B happening, which is also given to us. So we can just fill that in. Let's use a different color, 0.5. Well then, is it true? Are both sides equal to each other? If they are in fact equal to each other, that means that the given has no effect on the probability of A happening. And in that case, that means that the two events are independent. So now we know that the two events, event A and B happening, are not only not mutually exclusive, but they are also independent. So event A, for instance, has no effect on event B happening. Okay, so now we can go ahead and cross out some more answer choices. Cannot be determined, well, we just determined that we have enough information. So we're going to cross out E. And between C and D, we really want the one that says that they are, in fact, independent. So our correct choice over here is C. Okay, we're going to move on to the next problem. The distribution of colors of candies in a bag is as follows. If two candies are randomly drawn from the bag with replacement, what is the probability that they are the same color? Well, with replacement tells us that the events are going to be independent. One event does not have any effect on the other event because it was done with replacement. So that means that I can now add up all the possibilities of selecting two browns, which is 0.3, times 0.3. One event is independent of the other event, so if I go into the bag and try to draw out another brown, it will have the same probability. So it will still be 0.3. Now I'm going to add that with the probability of drawing a red. Okay, so I'm going to do 0.2 times 0.2. Or really, we can write it as 0.2 squared. And then a yellow. So we have 0.2 times 0.2. And really, I'm squaring it because I want 2 candies. If I had wanted 3 candies, I would be raising all of these probabilities to the 3rd power. And if I wanted 4, I would raise it to the 4th power, and so forth. All right, let's finish this up with green. So now I'm going to add the probability of randomly selecting 2 greens. 0.2 times 0.2. And lastly, for orange, we have 0.1 times 0.1. And I have started writing all of this in color, so let's change the first probability to brown to match its color. Not a common choice. All right, let's go ahead and find brown. Right there. Okay. It did not save the color that I wanted. Alrighty, let's do that again. Let's apply it. And there we are. All right, when we multiply all of this out and add them, we end up with an answer of 0.22, which gives us answer choice B. Okay. The next question, question number 3, says that the probability that a new microwave oven will stop working in less than 2 years is 0.05, and the probability that a new microwave oven is damaged during delivery and stops working in less than 2 years is 0.04. The probability that a new microwave oven is damaged during delivery is 0.10. So we have 3 pieces of information, and it says, given that a new microwave oven is damaged during delivery, what is the probability that it stops working in less than 2 years? Well, first of all, we have to define what our events are. So let's go ahead and define the probability of S as equal to randomly selecting a microwave oven that stops working in less than 2 years. Well, we don't really care about this part that says in less than 2 years. It could be in less than 1 year, it could be in less than 5 years. We don't really care about that part. It's just extra information, which is fine. We'll just include it for the sake of identifying what the probability of S is. Now, the probability of D is actually randomly selecting. It is always done randomly. A microwave oven that is damaged during delivery. And if we remember, our general conditional probability formula is probability of A given probability of B is equal to probability of A and B happening divided by the probability of B. So the given is always in our denominator. And in this case, I'm just going to rewrite it so that it matches our letters. So the given part is that it is damaged during delivery. So this part over here is our given. Okay, so it's probability of S given probability of D. The given is always to the right of this notation here. I'm going to set that as equal to probability of S and D happening, all divided by the probability of D happening. All right, so probability of S and D happening. So what is the probability that the microwave is not working in less than 2 years and is also delivered damaged? Well, it tells us right here that the probability that a new microwave oven is damaged during delivery and stops working in less than 2 years is 0.04. All right, that was easy. So we're just going to write that probability as our numerator. Okay, the second part of this is probability of D. Did they tell us the probability of randomly selecting a microwave oven that is damaged during delivery? Let's take a look at this. I'm highlighting this part that says that the probability of that happening is 0.10. So I'm just going to write that over here as my denominator. And actually, it's asking us to find the probability of S given D. Which is this part right here. And if we were to divide these two probabilities together, we end up with probability of S given D is equal to 0.4 or 0.40. Choice D. Okay, question 4. One student from a high school will be selected at random. Let A be the event that the selected student is a student athlete, and let B be the event that the selected student drives to school. If the probability of A and B happening is 0.08, and the probability of B given A is equal to 0.25, what is the probability that the selected student will be a student athlete? Okay, well, first off, let's write our conditional probability formula again. So it seems like the given part is that the selected student is a student athlete. That is the given. So we're trying to find the probability of B happening given A. Let's go ahead and write this formula down. And let's see what's given. So they tell us probability of B given A is actually 0.25. So we are going to write that right here. This part is given to us. What else is given? Probability of A and B. So this part highlighted in yellow is also given to us. We're going to fill that out as equal to 0.08. That is our numerator. And actually, we are trying to find the probability of randomly selecting a student that will be a student athlete. That is what the problem is asking us to find. What is the probability that the selected student will be a student athlete? Well, over here, if you add a 1 underneath the 0.25, and then we end up cross-multiplying, you can see that the probability of A is just equal to, I forgot to multiply this by 0.25, it's just equal to 0.08. And in order to get the probability of A by itself, we need to divide both sides by 0.25. So the probability of A is just equal to 0.08 divided by 0.25, and that gives us an answer of 0.32, which is answer choice C. Okay, let's move on to question number 5. A tropical storm is classified as major if it has sustained winds greater than 110 miles per hour. Based on data from the past 2 decades, a meteorologist estimated the following percentages about future storms. 20% of all tropical storms will originate in the Atlantic Ocean, of which 20% will be classified as major. 30% of all tropical storms will originate in the eastern Pacific Ocean, of which 15% will be classified as major. And lastly, 50% of all tropical storms will originate in the western Pacific Ocean, of which 25% will be classified as major. Right. The question is, based on the meteorologist's estimates, approximately what is the probability that a future tropical storm will originate in the Pacific Ocean, let's highlight that, and be classified as major? Well, all of them were classified as major, so nothing to cross out there, but actually I'm focusing on Pacific Ocean. So I only see 2 with Pacific Ocean, so I know that I can just ignore this first one. I'm going to cross it out. And we're just going to focus on the second and third pieces of information. So let's see. Well, we know from our earlier years of mathematical education that of tells us that we need to multiply this 30% as a decimal with 15% as a decimal. It's 30% of 15%. So we end up getting 0.045. And here it's of again, so we have 50% or half of 25%. And we end up getting 0.125. So you probably already guessed it, we are going to add these 2 probabilities up. So this is the probability that it's going to be classified as Pacific Ocean and be classified as a major. And there are 2 events happening, right? We can say that this is event 1 and this is event 2. When we add those 2 up, we end up getting 0.170, which is option C. All right, we're going to move on to our last question here. this says, a contestant's final winnings on a game show are determined by a random selection of a base amount and a possible multiplier. For the base amount, the contestant randomly selects one of 4 cards, where 2 cards are marked 1,000, 1 card is marked 2,000, and 1 card is marked 5,000. After choosing the card, the contestant randomly selects one of 5 chips, where 3 chips are red and 2 chips are white. If the selected chip is red, the contestant's final winnings are twice the value of the base amount. So that means that red is good. And let's see about white. If the selected chip is white, the contestant's final winnings are the value of the base amount. What is the probability that a contestant's final winnings are exactly 2,000? Well, this is a lengthier problem. This actually came from one of the previous AP exams for AP Stats. And I think what would be helpful is if we drew a diagram. So let's draw it out. Let's just say that we have 4 cards as stated. So draw out these 4 cards. Okay. And we have one is $1,000. Another one is $1,000 because there are 2 cards that are marked as $1,000. 1 card is marked as $2,000. And lastly, 1 card is marked as $5,000. Okay. Now we also have some chips. So we have some red and some white chips. So let's draw our red chips. Okay. This is going to be red, red, and one more red. And for the white chips, I'm going to draw them in black. And let's just label them as white. Drawing is not perfect because ideally they would all be the same size, but apparently they're not. Trying my best here. So let's take a look at what we have then. So it says, if the selected chip is white, the contestant's final winnings are the value of the base amount. This could be good actually, because we could get a $2,000 card and a white chip, and that will lead us to a final winning of exactly 2,000, right? So let's count how many possible solutions there are to get exactly 2,000. Well, first off, out of the 4 cards, we can get 2,000 by selecting the $1,000 card and then multiplying it with the red chip, right? That's 2,000. So we can do that with each of the $1,000 card. And then with 2,000, again, we can do that we can get $2,000 by selecting a white chip. So we really have 2 out of 4 cards that allow us to do this, and we have 3 out of the 5 chips. So let me go ahead and explain this in 1 minute, but that will get us to 6 out of 20. And again, they're independent events. So the 2/4 is talking about the $1,000 cards because there are 2 of them out of 4 cards. That's how we got 2 out of 4 for the first fraction. And we're multiplying that with the event of selecting a red chip. and there are 3 red chips out of 5 chips in total. So that's one possibility. But that's not the only one, as we talked about. The second possibility is actually selecting a $2,000 card. And there's only 1 out of 4 cards that says $2,000. And so if we select this card out of the 5 chips, we actually want the white chips. And there are 2 white chips out of the 5 white chips. Sorry, out of the 5 chips in total. And we end up getting 2 out of 20. And so you probably already guessed it. What we're going to do with these 2 fractions is that we're going to add them up. And when we add up 6/20 and 2/20, we end up with 8/20. And that gives us a decimal of 0.4, or choice E. Okay, so hopefully that was helpful. And if you have any questions, please feel free to find me after school on Thursday.